Good day everyone, I am Michael Jan Inario from Bsed Science 3, and for today's video we are going to tackle about the Thermodynamics Module 3 Measurement of Heat. Lesson 1 Heat Energy. In this task we are going to make 5 our own problem solving. Number 1. How much heat is required to heat 15 grams of water from 20 degrees Celsius to 70 degrees Celsius, and we're given a specific heat capacity of water. To find out the heat energy, we should use the equation Q is equal to mc delta T. And now we're looking for Q, which represent the heat energy absorbed or released. The mass is 15 gram. The specific heat capacity is 4.184 joules per gram per Celsius. And the change in temperature final minus initial is 70 minus 20 degrees Celsius. So 70 minus 20 is 50. 50 multiplied by 4.184 multiplied by 15 will give you 3,138 joules. So that's how much energy is required to heat up 15 grams of water from 20 to 70 degrees Celsius. 293.7 joules of heat is removed from 15 grams of aluminum, causing the temperature to drop from 85 degrees Celsius to 19 degrees Celsius. So what is the specific heat capacity of aluminum? So let's use the same formula now. What is Q in this problem? Q represents the heat energy in joules, but notice that heat energy is removed. So in this case, Q is negative. To 193.7, so when heat energy is released, we have an exothermic process. Q is negative. When a substance absorbs heat energy, Q is positive. We have endothermic process. The mass in this problem is 5 grams, so our goal is to calculate the specific heat capacity of aluminum. Temperature. So the final temperature now all we got to do is just calculate C19 minus 85. Keep in mind delta T is equal to the final temperature, and if we multiply that by 5, that's negative 330. So what we have is negative 330 times C, and that's equal to negative 293.7. So C is negative 293.7 divided by negative 330, and so the final answer is 0.89 joules per gram per Celsius. So that's the specific heat capacity of aluminum metal. So number 3, 500 joules of heat is added to 25 grams of iron metal at 22 degrees Celsius. Calculate that final temperature of iron metal because heat is added to temperature will go up. So let's start with this equation. Q is equal to mc delta C. So Q is positive 500 this time. The mass is 25 grams. The specific heat capacity is 45 joules per grams per Celsius, and delta T is the final temperature minus the initial temperature, which is 22. So first, let's multiply 25 by 0.45, and so that's 11.25. And next, let's divide both sided by 11.25. So what we have now is 44.44 is equal to the final temperature minus 21. So we need to add 21 to both sides. So therefore, the final temperature is 65.4 degrees Celsius. So number 4, 50 grams of an unknown material at 200 degrees Celsius was added to 100 grams of water at 25 degrees Celsius. So the final temperature of the mixture was 41.8 Celsius. So what is the specific heat capacity of the unknown material? So let's start with a picture. So imagine if we have a breaker of water currently at 25 degrees Celsius, and so we're gonna place a chunk of materials inside this container, and so this material is at 200 degrees Celsius. So let's see, the modem heat is gonna flow from the metal into the surrounding water molecules. Heat flows from hot and cold. So for the metal or the unknown material, the temperature changes from 200 degrees Celsius to 41.8 degrees Celsius. So heat is flowing out of the metal, and therefore Q is negative because it's an exothermic process. Whenever heat is released in the case of the water, the temperature increases from 25 degrees Celsius to 41.8 degrees Celsius. So the Q is positive. So now we need to set Q of the unknown material equal to Q of the water. The amount of heat energy that released from the metal is equal to the amount of heat energy that absorbed by the water, assuming there's no energy loss. So now, in order for this equation to be true, we need to put a negative sign on one side of this equation. So otherwise, it won't match. Q for the unknown material is negative and Q for the water is positive. So negative 5 is equal to the positive 5. So we need to introduce a negative sign on either side equation to make it work. So now, what we have the equation, we can go solve this heat transfer problem. So the left side, I'm gonna write everything that's associated with the unknown material. And on the right side, I'm gonna replace delta T with the final temperature. Minus the initial temperature, and everything related to water is going to be on the right side. So now let's plug in everything that we know. The mass of the unknown material is 50. So our goal is find the specific heat capacity of that material. And the final temperature is 41.8. The initial of the unknown material is 20. So mass of the water is 100. So the specific heat capacity of water based on the previous problems that we saw is 4.184, and the final temperature is supposed to be 41.8, and the initial temperature of water is 25. So now everything is good. So on the left, I have 41.8 minus 200 and take the result multiplied by negative 50, and so on the left, you should have 7,910 times the specific heat capacity on the right, which is the 41.8, and minus 25, so it's 16.8, and then multiplied by 4.184 times 100, and so you should get 7,029.12, and divided by that number by 7,910, and you should get a value of 0.889 joules per grams per degree Celsius. So that the specific heat capacity of the unknown metal, which is probably aluminum. So number 5, how much heat energy is required to melt 100 grams of ice? So the ethanol of fusion of ice is 6.1 kilojoules per mole. So what does the enthalpy of fusion tell us what this number means? That a mole of ice requires 6.1 kilojoules of heat energy to melt. So if that's the case, we can use that to calculate how much heat energy is required to melt 100 grams of ice. So starting with 400 grams of ice, which is still H2O, let's convert that to moles. The molar mass of water is approximately about the 18 grams per mole. Oxygen is 16 and hydrogen individually is 1. And there's 2 hydrogen atoms, so 2 plus 16 is 18. So now we could take the moles and convert it to kilojoules. So 1 mole of the ice requires 6.1 kilojoules of heat energy to melt. So it's going to be 100 divided by 18 multiplied by 6.1. So the answer is 33.4 kilojoules of heat. So here it goes. So we now in lesson 3, latent heat and phase changes. Let us do the numerical problem that involves all 3 states of water. So the problem is, a copper calorimeter can with mass 0.466 kilograms contains 0.0950 kilogram of ice. The system is initially at 0.0 degrees Celsius. A if 0.0350 kilogram of steam at 100 degrees Celsius and 1.008 atm is added to the can. So what is the final temperature of the calorimeter can and its contents? B. At the final temperature, how much are there of ice, water, and steam? So there are 3 subsystems here. So the ice, can, and the steam. And now let us talk what happened to each of the subsystem. So the steam will first need to condense into droplets of water. So steam condenses into droplets of water in a 100 degrees Celsius. So before it can lower its temperature. So how much heat it will release in the process of condensation? So that would be the heat of evaporation. Multiply by the mass. So we have here is 2,256 kilojoules per kilogram. Multiply by 0.035 kilogram. And that comes out to be 78.96 kilojoules. So let us put that answer so that we could remember. What's next? So the ice will first need to melt into liquid water before it can increase its temperature. So to melt into liquid water, how much heat it would need to absorb to break the bonds? So that will be LF, heat of fusion, times mass of ice. So that would be 334 kilojoules per kilogram multiplied by 0.095 kilogram, and that is 31.73 kilojoules. So if you compare these two numbers, you can see that the steam releases more than enough heat for the ice to absorb the melt. So what happened to the leftover heat? So the leftover heat will just go to rise the temperature. So then, what do we conclude here? That the final temperature must be between 0 degrees Celsius and 100 degrees Celsius. So let's call that variable TF final temperature. So let's write the complete heat transfer involved for each of the subsystem. So we have Q ice, we have 31.73 kilojoules. This is from melting plus M ice multiplied by CW, the final and the initial temperature initial, which is 0 degrees Celsius. This is for rising temperature. That's why we use a specific heat, and we use a specific heat of water because the ice is already melted into water here. And we have the can. The can also absorb heat to rise the temperature to some final temperature. So there will be mass of the can comply by specific heat of copper multiplied by T final minus the initial, which again is 0 degrees Celsius. Then we have the steam. Q of the steam releases heat into processes. First, the condensation, right, which is calculated here 78.96 kilojoules. Now, I should have put minus here because it's releasing heat. So therefore, I put the minus here. Plus now, it's gonna lower its temperature. So that mass of the steam is C water for water. T final minus 100 degrees Celsius. So this part right here is to lower its temperature. And notice that this quantity is going to be negative because the system is losing heat. So notice it is all negative because it's losing heat. So let's put it all together. So we have Q ice plus Q can plus steam. And that should all the 0 because we assume that the system is isolated system, meaning no heat transfer in or out of the system from the environment. So from here you can see that the only unknown is that TF. So you can solve for the final temperature. So let us write it down. 31.73 kilojoules plus M ice CW T final. I'm going to drop this 0 degree. M can C copper T final minus 0 degree C plus minus 78.96 kilojoules plus M steam CW T final minus 100 degrees C equal to 0. Okay, so now let us factor out all the TF. We have my C for water plus M can C copper plus M stem C water. That is M move all the numerical numbers to the right hand side. So we have 78.96 kilojoules minus 31.73 kilojoules plus M stem CW 100 degrees. So then TF. If you compute this quantity, so let's plug in some numbers. So there M ice 0.095 multiplied by 4.19 plus 0.446 multiplied by 0.319 plus 0.035 and multiply by 4.19, that equals 61.40 kilojoules. So, and this quantity when you calculate it to be 7,186, so your final temperature is 61.70 kilojoules over 0.7186 must have been kilojoules per degree Celsius and total to 86 degrees Celsius. And as you notice, that is from 0 degrees Celsius to 100 degrees Celsius that we all expected, and the all in a water mode. So the total of water will be the mass of the ice that all melted into water, and the mass of the steam have all condensed back into water, so that would be 0.95 kilogram plus 0.035 kilogram, that 0.13 kilogram. So there is 0.13 kilogram at 86 degrees Celsius. So for this scenario, the mass of the ice has been set to half kilogram while keeping all the other values the same. With half of kilogram of ice, it will need to absorb heat to melt. So that this question we can answer it would heat of fusion LF multiplied by the mass, which is half of kilogram, multiplied by 334 kilojoules per gram, which is 167 kilojoules. Now if you notice that the number is actually bigger than the amount of heat released by the stem in the condensation, and that number, if you remember, it was 78.96 kilojoules. So let us assume that the steam, in order to release more energy, lower its temperature from 100 degrees Celsius to 0 degrees Celsius. So how much heat released now? To answer that question, it will be the mass of the steam multiplied by CW, the heat capacity of water, 0 degrees Celsius minus 100 degrees Celsius. 0.035 kilogram multiplied by 4.19 kilojoules per gram multiplied by 100 degrees Celsius. Have you noticed is a negative because it's a heat release from that subsystem. So that is a negative number here, and that come out to be negative 13.67 kilojoules. So the total heat released by subsystem is 78.96 kilograms from the condensation plus 14.67 kilograms from lowering of temperature, which come out to be 93.62 kilojoules. So it is less than 167 kilojoules if all the ice would melt. What we can conclude about this? We conclude that only some factors of the ice melt, and the question is how much. So how much ice melts and depends on how much heat is received or absorbed from the steam subsystem. So Q for the ice will be the mass of the ice that melt multiplied by the heat of fusion. So this would be the heat and the ice absorb and melts, and that should be equal to the available that provided by the steam subsystem, so that 93.63 kilograms, and therefore the mass of the ice that melt is 93.63 kilojoules divided by the heat of fusion, which is 334 kilojoules per kilogram. So if you divide that out, and that come out to be 0.28 kilograms, which means that out of the half kilo of the kilogram of ice, only 0.28 has melted and turned into water. So at 0 degrees Celsius, what we have, some ice left over, which is half a kilo minus 0.28 kilogram, which is 0.22 kilogram of ice, and the water is from two components, is the 0.28 kilogram from the ice melt plus the steam that get condensed, which is 0.035 kilogram from the steam. So the total water is 0.315 kilogram for the ice, and this is for the water, and they are 0 degrees Celsius. They are in equilibrium. So we are in a scenario 3. The mass of the steam is to be 1 kilogram while keeping all the other values the same. So with this 0.1 kilogram, it would release how much heat? So we would have LV, the heat of evaporation, times the mass of the steam. So that 2256 kilojoules per kilogram multiplied by 0.1 kilogram, and that is 225.6 kilojoules. So it will release this much energy as it condenses as you remember the scenario number 1 with only 0.35 kilogram of steam, and the end we have the water, all the water at 86 degrees Celsius. So now with more steam, what will we expect? So we expect that temperature to be higher. But how high? Could it be higher than 100 degrees Celsius? So because it at 100 degrees Celsius, there is a phase change. So there is we have to do something differently. So let's first calculate out how much heat would be needed for the ice to melt and then rise to 100 degrees Celsius. So also remember the can also need to rise to 100 degrees Celsius. Heat for the ice to first melt and then go from the 0 to the 100 degrees Celsius. So remember, we did that calculation before. So the ice would need 31.73 kilojoules for melting, and then M ice plus C after 100 degrees Celsius minus 0 degrees Celsius, and that come out to be 31.73 degrees Celsius plus 0.095 kilogram multiplied by 4.19, the multiply by 100, and that come out to be 71.54 kilojoules. So it would take about 72 kilojoules to get the ice melt and then rise the temperature all the way to 100 degrees Celsius. So the can, so in order to get the can, multiply by the specific heat of copper and multiply by 100 degrees Celsius minus degrees Celsius. So that 0.446 kilogram 0.390 kilojoules per gram per Celsius multiplied by 100 degrees, that leave us with 17.4 kilojoules. So totally, to bring the ice and the can all the way to 100 degrees Celsius, we only need the sum of these two, 71.54 kilogram plus 17.40 kilogram, which is 88.93 kilogram. So what do we conclude here? If we compare this with these two right here, so the ice and a can need only about 89 kilojoules. So to bring it up to a temperature of 100 degrees Celsius, while the steam can release a lot more, so the steam does not need to release all that energy. So what we conclude here is the only sum of the steam need to condense. So the question is, how much? Well, how much the steam need to condense depends on how much the other subsystem, so which is the ice and the can, need to absorb. So Q of the steam condensed that release should be equal to 8,893 kilojoules, because that's how much is needed, and that is we write as LVX, the mass of the steam that condenses. So then we can calculate the mass of the steam that condenses. Not all of it are equal. So 88.93 kilojoules divided by LV, which is at 2256 kilojoules per kilogram, which come out to be 0.0394 kilogram. The only this much of the steam have condensed and turned into water at 100 degrees Celsius. So what's left is at 100 degrees Celsius. So we have a combination of steam. We start with 0.1 kilogram of steam. So if it condensed of 0.0394 kilogram, it equal to 0.0606 kilogram. This is still in the steam state. Next, we also have the water. Where's the water come from? The water is from the ice that melted, plus the steam that condensed. So the ice melted 0.095 kilogram, plus the steam condensed we just calculated to be 0.0394 kilogram, and that come out to be 0.134 kilogram. So that is water, and they are both at equilibrium and 100 degrees Celsius.